All right, everyone. So, multivariate lesson 2. Now that we've talked about some scatter plots and correlation analysis, this lends itself to a discussion of what we've been building up towards all semester long, which is regression, sometimes referred to as ordinary least squares regression, sometimes just multivariate or bivariate regression. So this tool, which could be used in a bivariate form, we really kind of focus on it as a multivariate tool. So it allows us to investigate relationships with more than two variables. So far, we really focused on a dependent variable, right? One phenomena, and an independent variable, or one cause. So including more than two variables allows us to control for other variables, and it allows us to make sure that we're not making spurious relationships because we've left explanations out. Here, a spurious relationship is one in which the association between two variables is really caused by something else, right? The third variable, or a lurking variable. So we're going to explore multivariate analysis using three basic tools. Correlation, or Pearson's R. We'll talk about that very quickly in a second. And then we're going to spend some time on multivariate regression, and then eventually we will talk about logistic regression. These two are very closely related. The difference is the dependent variable for logistic regression must be dichotomous, 0, 1, whereas for multivariate regression, we're talking about a continuous variable in that dependent variable. For all of these, multivariate correlation, regression, and logistic regression, the independent variables can be any kind of variable. They can be discrete, which is nominal or ordinal, and they can be continuous, which means ratio interval. Okay. So we talked about the general terms of Pearson's R last time, and what you've got in front of you here is an example of a correlation matrix. We've asked Stata to produce this correlation matrix for us. As you can see, it actually does look like a matrix. So in this case, this variable, which is tax rate per gallon, is right here on the top. It's also right here on the side. Notice that there's a certain symmetry to this table. In this case, we've got four variables, and what you're going to notice too is that the correlation of a variable unto itself is a perfect 1.0. This is true for all of these, and it doesn't fill in the top part of this table because it is symmetrical to this bottom part right here. So in this case, if you're going to read that first column, right, tax rate per gallon, you're going to read this first column right here, and let's see what the correlation is between this variable and tax rank. In this case, it's negative 0.84, which is actually fairly strong negative relationship. To craft total, it is negative 0.14, and to craft per capita, it is a positive 2.548. So, on a scale from 0 to 1, this is quite strong. These others are somewhat weaker, and obviously these two are negative, this one is positive. So it's not difficult to read these tables. What's important here is that if this were a simple bivariate table, you'd only have two variables. It'd only be out this far, right? You get tax rate per gallon and tax rank, and it would be much smaller. It would just be like these first four cells. But this is very easy to accommodate for multivariate settings. Obviously, in each case, you're only looking at one variable and its correlation to another variable at any given time. But this matrix can accommodate many different variables at once. Okay, so that's correlation. We're really much more interested in regression today, so we're going to talk about some very basic stuff. So regression, multiple regression analysis, or ordinary least squares regression includes your x, your y, and additional variables, control variables. Effectively, what it's interested in is finding an equation that best fits or approximates the data and describes the relationship between the independent and dependent variables. It is also interested in linear relationships. Regression is used to determine how one variable helps explain another. right? So how an explanatory variable explains a response variable. To get this explanatory relationship, we can draw a regression line. Again, this is looking at linear relationships. A regression line is a straight line that describes how the change in one variable, the dependent variable y, changes as the explanatory variable changes. It also allows us to predict a value of y given a value of x. And you can draw regression lines in your scatter plots. So that's what the regression program will do. Here's how you draw the line. The line is drawn using this very simple equation right here, which you might recall from high school or middle school. In this case, y hat, which is the expectation of that regression line, is created using this very simple algebraic equation, which is a plus bx plus e. A is the slope. Sorry, I got that backwards. A is your intercept. It's where you start the line. B is your slope. This is your value of x, whatever x is. And in this case, E is your error. That means where you make mistakes in fitting the line. So the observations that fall far from that line. Kind of think about it as this, as you would imagine a scatter plot. The equation for slope is located here. You're going to notice it's very similar to what we have seen before. You're standardizing x, standardizing y, you're summing that up, you're doing the same thing in the denominator. And intercept here is looking at the mean of y minus, you can actually solve for the intercept, the mean of y minus b, right, your beta coefficient, which is right here, that's your slope, multiplied by the mean of x. Okay, so what is the regression line? The regression line is a line with the minimum error between all points. What then is this error exactly that we're talking about? It is the distance from the expected value on that line to the actual value of the observation. So error in this case, right here, that's kind of the neat little addition to this simple algebraic equation, is the difference between your observed and your predicted dependent variable points. Okay, the slope, or beta, equals the rate of change in y when x changes 1 unit. Each additional degree, in this case, let's say we're looking at weather, each additional degree day predicts consumption of 0.19 more hundreds of cubic feet of natural gas per day. All right, so this example, this is just a little example here to illustrate one very important thing, which is that ordinary least squares regression, because it's conducting a standardization process like we've seen with z-scores and like we saw with correlation or Pearson's R, what it's doing is it's going to turn all of our data, right? It's going to look at the impact of x on y, but it's going to translate all that data into language of y. So the slope is always going to tell you what happens when there's a change in x and what it means for the change in y. So it's always going to be in the language of that dependent variable, that 1 unit change in x and what it means for change in y. In this case, that 1 unit change in degree days results in a 0.19 change in your dependent variable, in this case natural gas. Okay, the intercept of the regression line is when the value of that predicted line starts at 0. So it's where do you start that line. There's another important point here, which is r squared. It is the square of the correlation, or the amount of y that is explained by the variable x. Yes, it is related to Pearson's R. This is one of the reasons why we talk about correlation first, because that Pearson's R, when it's squared, gives us more information about the relationships that might affect the dependent variable. Okay, so some interesting facts about OLS regression. One, unlike Pearson's R, it is important that you identify which is the independent variable and which is the dependent variable. So which is x and which is y is going to matter here. And it also matters for when you ask Stata to conduct an OLS regression. There's a close connection between correlation and the slope of the least squares line. The least squares regression line always passes through x bar, or x mean, and y bar, or the mean of y. on the graph that you are plotting. Okay. Correlation coefficient, correlation R, describes the strength of a straight line relationship, and R squared is then described as how successful the regression was in explaining the dependent variable or the response variable. All right, some things to keep in mind here. Very important that you be thoughtful about what kinds of observations are in your data. One, influential observations are the kinds of observations that are likely to pull that regression line up or down. We need to know if they're there. We need to know if they're having a strong influence. These are closely related to outliers. So outlier could be just a point that's way far out there. It might or might not have a lot of influence on that line, but we need to look, and we need to kind of know what our data look like before we start conducting an OLS analysis. It is important to be cautious about extrapolating further than the actual data allows you to, right? So if you're creating an OLS regression line and it tells you that with this particular value of X, you're likely to get 1,000% increase in something, but you know that you can only go up to, your data only goes up to 100%, you have to be really cautious with that. Don't extrapolate beyond the actual values of your data. Second point to be careful with is, and some of you will recall me asking you not to average or use average data. For one, it robs you of variance in the model, and what this model is trying to do is trying to sort out those patterns, that trend, and it needs all the variance it can get. So when you use average data, what you're doing is you're sucking out all of the variation in your data set, and it's going to leave you with less information than what you'd like. Be careful with lurking variables, right? So that means all the stuff that you didn't account for, control variables that you left out, variables that the literature has already established as being important for that particular phenomena, all those things you need to be thinking about. That is not something that your Stata output is going to tell you. It's not going to tell you, hey, wait, you left out this really important explanation that all the literature has talked about. That's the hard part. That's the thinking part that you have to do before you actually conduct an OLS regression. And of course, always remember that association does not mean causation. These OLS regression models are going to tell you something about the association between these variables, but they're never going to spell out, hey, this is causing this. For that, you need to have a good thought process, strong theory to help identify causal relationships. All right, and with that, we are going to stop here and we'll pick it up again next time, talking a little bit more about OLS.